Thank you, Cosimo. Thank you for the kind invitation. I'm really honored and excited to be here and to be part of this workshop. And today, yes, I will speak about model-free and model-based control for articulated soft robots, but I will start with, it's not working, sorry. Okay, so I will start with a brief background. So traditionally, robots were mainly used in industries where the environment are structured and there are very few interactions or no interactions. No uncertainties, sorry. So here in this context, the main goal is accuracy. In this context, we have that compliance is seen as a drawback. And for this reason, both the design and also the control aim at increasing as much as possible the stiffness of the robot. But stiff robot leads to dangerous operations, potentially dangerous operations. So for this reason, we have that robots industries were caged, and the operation zone of the humans and of the robots were separated physically. Nowadays, as you already know, we aim at a different task. This tasks involving more collaboration and cooperation between humans and robots. In this context, we have that the environment is unstructured and there are interactions with a lot of uncertainties. So here the main goal is adaptability, and compliance came again, but in this case with a beneficial aspect. So compliance increases adaptability. So how can we add compliance into robots? There are two main solutions. The first one is to directly modulate the behavior of the robot, for example, using impedance control, or the reason why we are here today, that is the insertion of elastical elements into the robots. The second solution is known as soft robotics, and we can categorize soft robots into two main groups that are both inspired by animals. In one case, they're inspired by invertebrate, and the second case, they're inspired by vertebrate. So the first class is known as continuum soft robots, while the second one is known as articulated soft robots. And in the first case, the elasticity, the compliance is distributed along the wall structure of the robot, while in the second case, it is lumped at the joints. So we have elastic or flexible joints. In my talk, I will mainly focus in the second group, but at the end of my talk, I will also move towards the first class. So what can we do with soft robots? So as I said before, the main feature is probably adaptability, but there are also other features that are beneficial. And as in animals, soft robots can exploit the elasticity of their body to, for example, save energy, so to move efficiently, or to increase the peak performance of the robot, or to absorb shocks. So to control articulated soft robots, literature proposes several solutions, but most of them present one or two drawbacks. The first one is that they require an accurate model of the system. And the second one is that they usually rely on feedback. And feedback increases the stiffness. So the first issue is that the dynamics is hard to model, as we already see today. So an articulated soft robot can be modeled in this way. So if the robot is series elastic, these are the question, and we have that there is part of the dynamics that describes the motion of the link, and part of the dynamics that is related to the motors. In this case, we have the dimension of the state vector is double with respect to a traditional rigid robot. While if we consider variable stiffness robots, this is even more stressed because we have at least two motors per each joint. So we have that the state vector dimension is at least triple with respect to a traditional robot. Furthermore, we have that the mechanism, the elastic mechanism that connects the motors and the link is usually quite complex and introduces nonlinearities, delays, hysteresis, and so on. And all these aspects are even more stressed in the case of continuous of robot, where we have a dimension of the state that is virtually infinite. We have large information, and we have also a really high level of underactuation. So if we assume to have a reliable model, we can tackle very interesting tasks. For example, here we tackle the problem of time-optimal trajectory planning for articulated soft robots, including also some constraints on the compliant actuation. And here we consider the dynamics of a series elastic robot, and we parameterize the link path using a scalar coordinate has. So we can write an optimal control problem, including also boundaries both on the link side and on the motor side. And this is the problem. This problem can be recast through this nonlinear change of variables in a non-convex optimization problem with bilinear and quadratic constraints. And I will just show you some experimental results. So we tested this method on a 2 degrees of freedom planar series elastic robot. The actuation, the control is completely feed-forward. So we solve the optimization problem, and then we just use the solution as control input for our system, and we compare our planner with two other different planners. So our planner consider the wall dynamics of the robot, so the complete elastic dynamics. Then we use a traditional rigid planner and a planner that consider a chain of integrators with limit up to the snap of the link projector. So these are the results. The first one, the rigid case, basically is the fastest one, but actually it fails to fulfill the task because it does not respect the constraints, and it's also the trajectory that it tracks is different from the desired one. So without considering that one, the fastest one is the planner that considers the wall dynamics of the system. So the one that we propose, this is the video. So the one we propose is the right one, the next one. But as I said, usually the model that we have is not completely reliable and accurate. So the typical solution in this case is to add the feedback component to increase the robustness of the controller. But as I just said, feedback increases the stiffness. And I can show you that with a very simple example. So in this case, we are considering this mass spring damper system, whose dynamics is this one. The input is theta, and the stiffness is K. So if we use a very simple controller that is a proportional controller, we have that the total stiffness of our system is increased. And I can show you also an experiment of that. Here we are considering a planar robot with a variable stiffness joint. We have 2 degrees of freedom, and we are commanding a soft behavior. On the left-hand side, we are using a feedback control. On the right-hand side, feed-forward control. And as you can see on the left, you have that despite the fact that we commanded the soft behavior, the robot behaves as stiff. While using a feed-forward control, we do not have that issue. So now the question is, we built more complex robots that are more expensive and also more difficult to control. But at the end, we have basically a traditional rigid robot. So why we do that? To avoid these problems, the one solution that we try is to use model-free feed-forward technique. So basically learning-based methods. And in particular, we tried iterative learning control. So Here with iterative learning control, what we do is to repeat the same task with the robots, and we store the control input and the error of the previous trials, and then we use this information to update the control action for the next trial, for the next iteration. And at the end, we have that the robot is able to perform the desired task. So very briefly, this is the controller. We have an initial guess that can also be model-based if you have a model. Then we have an updating load that is based on the previous trial error. And finally, a very small gain for the feedback to avoid an alteration of the stiffness. We can also prove the convergence of the iterative procedure. I will skip that. And this is an experiment. Here we're using a delta robot with 3 degrees of freedom, and each joint is updated by variable stiffness actuator. The trajectory is simply moving the end effector of the robot through these 2 obstacles. It is shown manually to the robot moving the end effector, and then the learning process starts. At the beginning, the robot is not able to pass the obstacles, but then we'll go directly to the result. We have that the robot is able to track the desired trajectory. So problem solved. So we have that we are able to track a trajectory with articulated soft robots with a model-free approach that is also fit forward. But actually, we still have some issues because learning-based methods come also with generalization issues. So we have that the control action that we learn depends on some information. For example, it depends on the stiffness profile that we use during the learning, on the velocity of the trajectory, and also on the trajectory itself. Of course, if you change just one of these parameters, we have to repeat the learning process. I can show you one example here for the stiffness. Here, using the previous control, we learn the trajectory with this 6 degrees of freedom R. We learned it with a soft behavior. Then, using the same learned control action, we try to track the same trajectory by changing the stiffness behavior from soft to stiff. And the result is this. So we have a huge tracking error. So to avoid that, what we can do is to start again from the model. So we want a model-free approach because usually the model is not completely accurate, but actually we can exploit the information that we have about the model. So we know that this robot can be modeled in this way. And changing the controller from a position control, the previous one was a position control, to a torque control, we can prove that under some assumptions, the dynamics of the system, or in general of a system that can be written in that way, can be decoupled. And we have then a part of the dynamics that describes the motion of the link, and a part of the dynamics that describes the stiffness relation. So now we have 2 different inputs, and we can use an iterative procedure on the input that control the link motion, and a different controller for the stiffness regulation. And this is the result, same experiment as before with the new controller. Now we have that even though we change the behavior, the stiffness behavior from soft to stiff, the performance are basically the same. And we have also that the stiffness behavior is still preserved because the controller is fit forward, basically. Moving on, we can also study the problem of changing the velocity of a learning trajectory. In particular, if we have a trajectory, we can time scale it, and this way we can track it with a slower motion or also faster motion. Now the problem is to find the minimum number of examples that provide enough information to generalize, and then also to write an algorithm to do that. So in the previous case, in the stiffness case, one example, one learning process was enough to generalize with respect to the stiffness. In this case, we need more examples, and in particular, we need 5 of them, and I will show you just in a moment. So again, we start from the modeling. We know that this kind of system can be modeled in this way, and we can time scale the trajectory. And then I'll skip all the steps. This is the result. This part of the dynamics of the system is unknown, except for the input, the torque, tau, that can be learned through iterative learning control, or you can use your favorite controller. It does not matter. And then the time scaling parameter. So we can rewrite it in a more compact form, that is this one, where Xi collects all the unknown dynamic terms. And then we can stack different examples in a matrix form. And what we obtain is this one. So we have this P matrix that must be inverted to derive the control action. But P is a van der Waals matrix with 5 columns, so 5 rows are enough. So 5 examples are enough for P to be invertible. So with that, we have that the algorithm is very simple. So given a new time scaling factor alpha, we can simply invert P and multiply it by for U that collects all the torque examples, and we'll obtain the control action to track the same trajectory with a new time scaling factor. I will show you one simulation result. Here we're using a backstab robot to perform a drum playing task. And we acquire 5 different control action for 5 different time scaling factors. And then we can generalize for new time scaling factors. And so this is the result. The red dots are the performance of the 5 examples. And this is the generalization. So the blue line are the performance of the generalized control action without repeating any learning process. So we have that the performance are comparable to the one of the example provided. Okay, at this point, we would like to move towards continuum of robot. So one of the problems that we said just before about continuum of robots is the high level of abstraction. So the question we asked ourselves was, how can we control a system that presents elastic joints, but just a few of them are actuated and many of them are passive or unactuated? So in this case, the dynamics can be written in this way, where S is a matrix that describes this under actuation. Again, we use an iterative controller, and we can also prove its convergence. This controller requires a fixed relative degree. And for this reason, we have to study how the relative degree changes for this system. So we have that, of course, the relative degree changes depending on the output function, but also there are some conditions that can be drawn on the inertia of the robot and also on the motion of the system to fix the relative degree to 2. So respecting this condition, we can try our controller on a system of this type. So in this case, we are considering this 3 degrees of freedom robot, where the first joint is active while the 2 other are unactuated, and we are tracking a minimum jerk trajectory. Again, the same robot, but in this case, we have a sine trajectory, and we have also this unperceived disturbance, that is this weight that is attached to the tip of the robot, the end effector of the robot. We can also use a planar robot with 2 actuated joints and 2 passive ones, and here we are tracking a planar circumference. At this point, we can move towards continuum of robots, and in particular, we focused on the 2D soft inverted pendulum. That, if you do not know that, please check the paper, the CDC 2020 paper by De La Santina, very interesting. And so, again, we want to use iterative learning control to control this system. This system is a single input, single output system with a fixed relative degree equal to R. And we can write its dynamics in with this formulation. So we can prove that an iterative learning controller is able to converge when these dynamics present a G term that is constant. So using this controller that presents a feed-forward component and also a feedback component and a forgetting factor Q, then if this condition is satisfied, I will skip the proof, but if this condition is satisfied, we have that the tracking error of the output is upper bounded. And in particular, we have that if the forgetting factor Q is equal to 1, we have a zero tracking error. But in our case, for the 2D soft inverted pendulum, we have that G is not constant, is actually a G of X. So we can change our controller from the previous one to this new one, where we have a new control input V. So we can apply iterative learning control on V. And if the previous condition is satisfied, then we have that the convergence is guaranteed. But we have this difference, and it is that the previous controller was completely model-free, while this one has a model-based component. So we have that U depends on G of X. So using this controller, we can try to control our system. The dynamic model is this one. The output is the orientation of the tip of the robot. The relative degree is equal to 2. And with this parameter of the stiffness, we have 3 equilibrium points that are 2 stables, the lower one and one that is unstable. And the task is to track this minimum jerk from the lower stable equilibrium point to the upper unstable one. So this is the result for the learning. As you can see, we have a 0 error after third iteration, but we do not have any monotonicity because this was not proven. So the first trial, this is the performance of the robot. Basically, it fails to achieve the task. While at the last iteration, we have that starting from the green position, it is able to move to the blue one. Okay, to conclude, I presented several control algorithms to control articulated and continuous soft robots. This algorithm mix model information and model-free methods to try to take the best of the two worlds. And they are mostly feed-forward, so they are able to preserve the compliance of the robots. Future work will focus on the extension of these methodologies to soft robots. In particular, I studied the case of a single input, single output soft body, but not the case of multi-input, multi-output robot. And we will also focus on the experimental validation of this theory. In addition, we will also try to apply all this theory to the new H2020 project, Natural Intelligence, that aims at use robotics for environmental monitoring, so to monitor natural habitats. Well, thank you very much for your attention. I would like to thank the organizer for inviting me, and also all the people that collaborated with me for this research. If you have any question, please, you can use my email address or just ask them right now. Thank you.
So thanks Franco for the talk, and we already have 2 questions. So the first is Alessandro De Luca.
Yes, Franco, very nice presentation. I have a huge number of questions, so I will limit myself to only 2. One is when you're using uniform time scaling in order to acquire, if I understand correctly, you need 5 tests in order then to acquire the torque for any other scaling. Is it correct?
Yeah.
And because I remember you're quoting an old paper of mine on joint elastic, on the joint elastic case, where we had a B quadratic formula that whose solution provides the new torque for any value. So my understanding is that in your model you have other extra term, including damping, that requires these 5 tests, correct?
Yeah.
Yeah.
So in our case, for this formulation, basically the number 5 came from this matrix, from the P matrix, and we need to invert P in this step. And since P, I mean, it must be square and non-singular, and for that reason we need 5 examples. So we need 5 rules. But
from there on, if I give you another timing, which is a different scaling, without any other new computation, you can provide the torque.
I mean, the new computation is just this one. So with this computation, without a learning process, you can track the same trajectory with a new time scaling factor. The point is that the performance depends on the performance of the examples. So if the examples have a perfect tracking, so also the generalization will be a perfect tracking, with a perfect tracking.
The other question is on one of the latest slides. It's surprising that you have this non-monotonicity. Why is that of the convergence? Yeah.
So this comes from the proof, actually. With I don't remember exactly the step where it comes from, that we have that we can prove that the error will be 0, but we cannot have any information about the monotonicity of the process.
But I'm saying you showed a rate of convergence that after 3-4 iterations. Yes. So why you have an increase of error there? So you're not I mean, you cannot prove contraction unless you're proving contraction over a number of iterations. So in block of iteration. But if you do, I'm contracting the error from one iteration to the other, then this is impossible, if I understand correctly.
It is possible to have this kind of error.
That you have a divergence and then a convergence again. I mean,
I can comment on it since I was also involved. Yes, it's on case steps, so it's not from one step to the following one. So I think, I mean, the first author is not here to defend himself, but if I'm not wrong, what it's done is to bound the Kate step.
Or take it, as Alessandro said, groups, because then you could have in the average that you have a decrease in kind of behavior.
Yeah.
Because you have a lot of optimization algorithms that have non-monotonic convergence, but in fact they achieve this relaxing condition over a number
exactly
of steps. So then you converge. Okay, thanks. Well, anyway, I will ask you further a question offline. Okay.
Sure.
Thanks for the presentation.
So next question is from Stefan.
Also from my side, congratulations for the very, very nice presentation. I haven't grasped all the details. I was puzzled about this van der Monde matrix coming up, so I would like to read more details about it. I don't want you to bother you with this. Could you please put the reference of give reference to the organizer so that we have a central point where we can find the references? That would be great. And if you have an answer, because if you go intuitively why this van der Monde matrix appears, which gives you these 5 things, is not very clear to me.
Yeah, because I just skipped all the steps. So going back. So here. So basically, the steps are quite easy actually. So we just have to invert the dynamics, and basically we differentiate the first equation a couple of times, and then we rewrite all the complete dynamics on Q. So we remove the theta variable, and we have that differentiating the trajectory. When you do that, I remove the step here. I'm sorry for that. So you have that the time scaling factor comes out from the derivative. It multiplies linearly the derivative. Since we need to differentiate 4 times the link position, we have this.
Yeah,
I don't know if you can see my mouse.
Yeah.
And you have this term. That
but why do you need to differentiate 4 times? That's not clear. I don't see it immediately. Oh, because of you have the two equation of. Oh, I see now. Okay, now I see.
Okay.
Yeah.
Okay.
Yeah. Okay. Clear. Thanks.
No problem. Thank you.
Thanks.
Okay, so I am. I think the time is up. We have another questions from Guaraci, so maybe Franco can answer to the into the chat while we close up the workshop.
Yeah, actually, I cannot see the question. Where is it? Yeah.
So yeah, I can read
Okay,
it very quickly. So the unstable internal dynamics was not a problem to find a solution in the under-actuation case?
No, actually, it was not. So we didn't encounter any problem in that direction, and yeah.
Okay, thanks, Franco. Yeah, I would like to also stress something about your work about under actuations. It's super cool, and I look forward to see the new iteration. I want to stress, I think, because it's a point that should that I think applies to all the 4 control talks that we saw so far. Today, that it's that what you have there, you are validating it with a robot, which is an articulated soft robot. But once you start assuming some under actuation, the models, it's really becomes almost equivalent to a continuum soft robot, at least under some assumption and under some under actuation pattern. So you are validating to experiments on an articulated soft robot, but there's many of the techniques that we saw today. I think is a great potential to be applied to the continuum case. Okay, Stefano raised the hand again.
Because I think what you said, it's very relevant for the whole discussion of a number of talks today. Because I think at the end of the day, every control, I mean, if it's controllable, if you can reach and do something, so to speak, right? What nature does is that, you know, you basically have a model. You try to use as much as you can the model. So what you don't know, you learn it, as Franco very nicely and elegantly showed, right? So at the end of the day, also, if you have elasticities, whatever dynamics you have, what you can do is, if you can reach something, you just use as much information as you have, and you iteratively learn it. That's what animals do in the animal kingdom. So that's the way to go. So that's why I think it's all in everything which was presented today fits in that respect, I think. So just a closing comment.
If I may add something about under actuation. This was in one of the slides that I skipped. In fact, these flexible systems, as well as a rigid system with passive joints under gravity, they are under actuated. I mean, if there are some missing command, but they are linearly controllable, thanks to the potential energy of elasticity or to the potential energy due to gravity. So exactly. the real, for me, notwithstanding the fact that many say, okay, this is an under actuated draw. I mean, the real challenging task is, for instance, controlling a rigid robot, planar in the horizontal plane, with two passive joints. And this is the hardest control problem I ever seen, in fact, because you don't have this linear controllability. So you cannot rely on any approximation. I mean, we used nilpotent approximation, for instance, and it was a mess.
Exactly. Very good point, Alexander.
Yeah, and I think this is, I mean, probably the reason why, as you just said, the reason why soft robots, in a sense, are in the practice so simple to control, is because there is this, there is potential field and also some damping acting that is really acting on all the degrees of freedom. So they are infinite, but there is this action that it's there everywhere, and it acts as a stabilizer. While in the planar rigid case, without gravity, it's really like you have to do all your work through control.
But by the way, Franco, this was another question. When you say that you are having some joints are elastic and actuated, and some are only passive but elastic, what do you mean? That there's a spring between the two links connecting, or it's just that you switch off the motor on that joint?
So
it's an elastic
you
joint.
mean for the experiment, or
I mean, for the model.
So the model is there is a spring between two joints.
So you have only one variable at the passive joints, which is the deformation of the spring.
Exactly.
You don't have two variables, one of the motor which is switched off, and one for the link, and then okay.
For the experiment, we had to avoid that. So we didn't have a robot in that way. So we used a series elastic robot. Basically, we commanded the motor position equal to the I mean 0 motor position, and then we used that as a spring.
Okay.
Yeah.
Fine.
Okay. So I think we had also a very impromptu, nice discussion at the end that worked quite well, I think. So that's I think then marks the end of our workshop today. So yeah, I and the name also from Brandon and Sasha, so all the organizer, I want to thanks a lot to all the speakers. I think you all made this workshop, I think, a super cool one and exciting one to attending. I don't know if Brandon, you want.
Congratulations to the organizer. It was great. I really enjoyed it. Thanks a lot.
Very nice.
Thank you.
Thank you very much. Very nice presentations and organization. Thank you.
Thank you. Yes.
Thank you all as well from this side. Thank you very much.
By the way, today in Rome is a holiday. It's St. Peter and Paul. So this is why I'm home, because the department is closed.
Okay, so thanks for being here despite the holidays.
And let's hope the next time there is a workshop like this will be in 3D with multimodal interaction.
Okay. Thank you very much. Have a nice day and see you soon.